In 1929, a single engineer took a weak, outdated locomotive and made it 50% more powerful, without adding fuel, without making it bigger, without changing the engine. And when they tested it, the numbers came back impossible. That shouldn't have been possible. Nobody had ever gotten more power out of less machine. The physics didn't allow it. The tradition didn't allow it. And the budget certainly hadn't asked for it. 3 months later, that same tired locomotive rolled out of tours and onto the test track. The dynamometer car, the rolling laboratory that measured everything, started recording. The numbers it printed didn't make sense, not because they were bad, because they were impossible. Power output up by nearly 50%. Coal consumption unchanged. A locomotive that should have been retired was now outrunning engines that cost 3 times as much to build. One engineer in the room that day reportedly said nothing. He just walked to the window and looked at the track for a long time. His name was André Chapelon, and what he had just proven would haunt French railways for the next 30 years. But to understand what he did in that workshop, and why the government that benefited most from his work would later order his greatest machine destroyed, you have to go back further. Back to a problem nobody knew they had.
For over 100 years, engineers kept making the same mistake. More power, build it bigger. Faster, add pressure. Struggling on a grade, burn more coal. It was the logic of brute force. And for most of railway history, it worked. Engines grew from small, clattering machines that could barely pull their own weight to giants like the Union Pacific Big Boy. 600 tons of steel, 6,000 horsepower, long enough to wrap around a city block. The formula seemed unbeatable, but somewhere inside every one of those locomotives, something was going badly wrong, and nobody was looking for it. Here is the number nobody was measuring: efficiency. A typical steam locomotive in the 1920s converted roughly 6 to 8% of its fuel into actual motion. The rest, more than 90% of every ton of coal shoveled into that firebox, vanished. Heat lost through the exhaust, energy wasted in friction, power strangled inside pipes too narrow to carry it. To put that in context, a modern car engine wastes about 60 to 70% of its fuel. The steam locomotive of that era was doing worse, far worse. Engineers knew the number, they just didn't think it could be fixed. Steam was steam. You burned it, it pushed a piston, the piston turned the wheels. The losses were considered natural, unavoidable, the price of doing business. So instead of asking why the energy was disappearing, they kept doing what they had always done. But no one had actually seen the problem. Until him. They made the boiler bigger, they raised the pressure, they hired more firemen to shovel faster. The locomotive wasn't a system to be understood. It was a machine to be scaled up.
And for a century, that thinking went almost completely unchallenged. Almost. Because in a small research office at the Paris-Orleans Railway in 1925, a 33-year-old engineer with a background in mathematics and artillery had started asking a different kind of question entirely. Not how big should the engine be, but where is the power going? And this is where everything changes. André Chapelon was not the kind of engineer who filled a room. No grand speeches, no dramatic gestures. When colleagues argued over designs in the meeting room, he was usually the quiet one in the corner, the one taking notes, asking small, precise questions that nobody else thought to ask. He had served as an artillery officer in World War I, and artillery teaches you something that most engineers never learn in a classroom: the difference between a system that looks powerful and a system that is powerful. A gun that loses pressure before the shell leaves the barrel is not a powerful gun. It is a waste of metal and mathematics. Chapelon brought that same thinking to railways. When he joined the Paris-Orleans Railways Research Division in late 1925, he did something his colleagues considered slightly eccentric. He didn't start by drawing new locomotives. He started by measuring old ones. He attached instruments to engines already in service, pressure pages at every stage of the steam circuit, flow meters on the pipes, and then, in a detail that tells you everything about the man, he used high-speed stroboscopic photography to watch what happened to steam inside the cylinders while the engine was running at full speed. Nobody had done this before, not because the technology didn't exist, because nobody had thought it was worth doing. What he saw changed everything. The steam was choking, and once you see it, you can't unsee it. From the moment it left the boiler to the moment it was exhausted into the air, the steam was fighting its way through passages that were far too narrow, around bends that were far too sharp, through valves that opened far too late and closed far too soon. Every component had been designed by tradition, not by physics. Every dimension had been copied from the locomotive before it, which had copied from the one before that, going decades.
The locomotive wasn't underpowered, it was suffocating. Chapelon described it this way. Imagine an athlete in peak physical condition, asked to run a marathon, but breathing through a straw. The lungs are fine, the legs are fine, the engine is fine. The problem is the airway. Remove the straw, and the athlete runs free. The question was whether anyone would let him try. His supervisors at the Paris-Orleans Railway gave him a test case. Not a new locomotive. They weren't ready for that. Just an old Pacific, locomotive number 3566. A 10-year-old machine with a reputation for mediocrity, assigned to secondary runs because nobody trusted it with anything important. It was, in every way, the perfect subject. Because if Chapelon was right, it wouldn't matter that the engine was old. Age wasn't the problem. The plumbing was the problem, and plumbing could be fixed. He spent the next 3 years redesigning every inch of the steam circuit. He quadrupled the volume of the low-pressure steam chest. He enlarged the steam passages until they were almost unrecognizable. He fitted a new exhaust system designed with a Finnish engineer named Kyösti Kulala, combining both their names into what would become known as the Kilchap exhaust, that used the Venturi effect to pull exhaust gases out of the cylinders cleanly and completely, eliminating the back pressure that had been strangling performance for a century. He didn't touch the boiler, didn't raise the pressure, didn't change the wheels. He just removed the straw. And in November 1929, locomotive number 3566 rolled out of the Tours workshop and answered the question nobody had thought worth asking. Then they tested it. The dynamometer car never lies. What they got shouldn't have been possible. It is a sealed laboratory on wheels, towed behind the locomotive, measuring everything in real time. Drawbar pull, speed, steam pressure, coal consumption, every number printed on a continuous paper roll, second by second, mile by mile. You cannot argue with a dynamometer car. You cannot charm it or politically maneuver around it. It records what happened, nothing more. On the morning of the first full test run, the paper started moving. The engineers watching it went quiet. Locomotive 3566, the tired, mediocre Pacific that Foreman had spent a decade apologizing for, was producing 3,000 indicated horsepower, nearly 50% more than its official rating, more than locomotives that had been built new at 3 times the cost in the same year. And the coal consumption? Unchanged. Not slightly better, not marginally improved. The same amount of fuel was now producing half again as much power, which meant in the language of railway economics that every ton of freight this locomotive pulled just got dramatically cheaper to move. There were 3 reasons for that number, and one of them was quietly the most important. The enlarged steam passages meant pressure wasn't bleeding away before it reached the cylinders. The Kilchap exhaust meant back pressure wasn't fighting the piston on its return stroke. And the redesigned valve timing meant steam was being used completely, not partially, before being released. 3 problems, all invisible, all ignored for 100 years, all fixed by one man who had simply decided to look. Word spread through the Paris-Orleans Railway faster than the locomotive itself. Other railways sent engineers to Tours to read the test results, then to reread them, then to ask quietly whether Chapelon could do the same thing to their engines. The answer was yes. Engineers from Czechoslovakia reportedly sought his consultation on their own locomotive programs. Over the next several years, 3 additional series of Pacifics were rebuilt using the same principles. Each one produced results that the industry had no previous framework to explain. A British engineer who reviewed the data later described Chapelon as a genius, head and shoulders above his contemporaries. The Americans quietly took notes, but inside the Paris-Orleans Railway, and later inside the SNCF, the newly nationalized French railway that absorbed it in 1938, something else was happening, something quieter, and far more dangerous to Chapelon's work than any failed test result. The bureaucracy had started paying attention. By 1946, André Chapelon had been quietly rebuilding locomotives for 17 years. No headlines, no ceremonies, no government contracts bearing his name, just a man, a workshop, and a dynamometer car that kept printing numbers nobody could explain. But 1946 was different, because in 1946 he finished the 242A1. It had started as locomotive number 241.101, a heavy 482 that the SNCF considered a failure.
too slow, too inefficient, not worth the coal it burned. The kind of machine that ends up in a corner of the yard, waiting for a decision nobody wants to make. Chapelon made the decision. He would rebuild it completely. Not just the steam passages this time. Everything. The cylinders, the exhaust, the valve gear, the thermal insulation. He applied 17 years of accumulated knowledge to a single machine and asked one question. What is the absolute limit of what steam can do? It took years. The war interrupted everything. Parts were scarce. The workshops were cold and understaffed. But in 1946, the 242A1 rolled onto the test track, and the dynamometer car started printing numbers that changed the argument entirely. 5,500 indicated horsepower, recorded under test conditions, and repeatable. Not a spike, a documented, measurable ceiling. Not a brief spike on a downhill run. A steady, controlled, repeatable 5,500 horsepower at the drawbar. The kind of power that moves mountains of freight without breaking a sweat.
This one machine was producing more power than most modern systems at the time. The 242A1 beat them, and that's when the problem stopped being engineering and became political. A rebuilt steam locomotive, built on a frame that had once been considered scrap, was outperforming the brand-new electric future of French railways by 1,500 horsepower. The power-to-weight ratio, roughly 40 indicated horsepower per metric ton, has possibly never been matched by any steam locomotive built anywhere in the world before or since. The international railway communities sent observers. The tests were later described as the most extensive and complete ever done on a locomotive, opening, in the words of one engineer, absolutely virgin fields of experiments. And somewhere in Paris, in an office with thick curtains and a long conference table, a group of SNCF executives read the test report and felt for the first time something that had nothing to do with engineering. They felt embarrassed. They didn't celebrate him. They tried to bury him. France in 1946 was a country trying to forget the past 4 years had happened. The German occupation, the rationed food, the bombed infrastructure, the national humiliation. The government wanted one thing above everything else: to look modern, to look forward, to look like a nation that had moved beyond coal and fire and the grinding mechanical world of the 19th century. Electric trains fit that image perfectly. Sleek, clean, silent. No smoke, no soot, no fireman with a shovel, just a driver in a clean cab pressing a button. Steam was the past, and the past was exactly what France was trying to bury. André Chapelon's 242A1 was not just inconvenient, it was politically dangerous, because it proved, with dynamometer data that could not be argued with, that the modern electric trains SNCF had spent hundreds of millions of francs developing were less powerful than a rebuilt steam locomotive. The executives didn't ask Chapelon to explain his results. They asked him to stop producing them, because he was proving something they couldn't afford to be true.
What happened next is one of the most extraordinary moments in engineering history. SNCF didn't cancel Chapelon's work outright. That would have been too obvious. Instead, they gave him a new assignment. Build us a production locomotive, they said, based on your principles, something we can actually use. Chapelon began work immediately. He designed the 241P series, a heavy Pacific incorporating the most advanced steam technology he had developed. It would be efficient, it would be powerful, it would validate everything the 242A1 had proven. Then the specifications came back from management, with modifications. Remove this feature, simplify that system. This component is too complex for standard maintenance crews. Each change on its own seemed reasonable, practical, the kind of sensible compromise that keeps projects moving. But Chapelon recognized what was happening. Each modification was removing one of the elements that made his system work, not randomly, systematically. They were asking him to build a worse locomotive, on purpose. The 241P series was built. It was a capable machine, far better than anything designed by committee. But it was not what the 242A1 had proven was possible. It was a deliberately hobbled version of his best work, approved by men who had read the test reports and understood them well enough to know exactly what to remove. Between 1946 and 1953, Chapelon designed several more locomotives, each one pushed further than the last. A radical 6-cylinder machine, the 160A1, with cylinders arranged in configurations that had never been attempted.
because the French loading gauge was too narrow for conventional placement. 2 high-pressure cylinders tucked between the second and third driving axles, 4 low-pressure cylinders at the front. An engineering solution so unconventional it looked like a mistake until you understood the physics. The test results were buried.
Not published, not discussed at engineering conferences, not sent to the international bodies that had been so interested in the 242A1 just years before. Buried in a filing cabinet, in an office, in Paris. Because the 160A1 was by every measurable standard more efficient than the electric locomotives SNCF was rolling out across the network. And that was a conclusion that the French government had already decided it did not want to reach. His final design, a revolutionary 210-4 freight locomotive, Class 152, that would have taken everything he had learned across 30 years and built it into a machine from scratch, got as far as 2 partially constructed frames before the order came to stop. The frames were scrapped before they were finished. 1960. On a gray morning in 1960, workers at a French railway depot cut apart the 242A1 with acetylene torches. It took several hours. The steel was thick. The machine did not come apart easily. When it was done, the pieces were loaded onto flat cars and sent to a smelter. The greatest steam locomotive ever built, the machine that had outrun electric trains, that had printed numbers the international community called unprecedented, that had proven steam could compete with anything into the 1980s, was melted down for scrap. No museum was offered the chance to preserve it. No heritage railway made a bid. No ceremony was held. At his retirement in 1953, Chapelon left behind colleagues who understood what had happened to his work. The record spoke for itself. He didn't need to explain why. Everybody in that room knew his greatest locomotives had been scrapped. Everybody knew his best designs had been canceled. Everybody knew the reports had been filed away in drawers that nobody was meant to open. A man who had given 30 years to proving what was possible had spent the last decade of his career watching the proof get quietly erased.
Here is what they could not erase. In 1938, 8 years before the 242A1, a British engineer named Nigel Gresley had quietly fitted a Kyle Chap exhaust to his A4 Pacific locomotives on the LNER. The same exhaust system Chapelon had developed, the same physics, the same invisible fix to a problem most engineers didn't know existed. On July 3rd of that year, LNER locomotive 4468, named Millard, reached 126 miles per hour on Stoke Bank in Lincolnshire. It is still the fastest a steam locomotive has ever moved under its own power, anywhere in the world, in any country, in any era. The world speed record for steam, held to this day, runs on André Chapelon's exhaust. His ideas didn't stop in Britain. An Argentine engineer named Livio Dante Porta studied Chapelon's work and carried it forward into the second half of the 20th century, keeping advanced steam running in South America long after Europe had abandoned it. A South African engineer named David Wardale built what became known as the Red Devil, a rebuilt locomotive using Chapelon's principles that shocked South African railways in the 1980s with performances nobody had thought steam could still produce. Some engineers who later worked on French high-speed rail programs had studied Chapelon's methods. Whether his specific findings shaped TGV development directly remains a matter of debate among railway historians. The science he had developed in service of steam was absorbed into the machine that replaced it. He died in 1978. He had lived long enough to see the TGV begin its runs, long enough to know that France had built something extraordinary out of electricity and precision engineering, long enough to know that he had been right about steam too, and that it hadn't mattered. If you've ever wondered why the best ideas don't always win, this is it.
There is a particular kind of frustration reserved for engineers who are correct. Not the frustration of failure. That is clean, understandable, something you can learn from and move past. The frustration of being right at the wrong moment, of proving something so completely that it becomes inconvenient, of watching the evidence get filed away, not because it was wrong, but because the people who read it had already decided what the answer should be. André Chapelon never designed a locomotive from scratch. He was never given that chance. He spent his career rebuilding other people's machines, proving with each one that the limits everyone accepted weren't limits at all. They were just habits nobody had bothered to question. His masterpiece was cut apart with a torch. His greatest designs were canceled mid-frame. His reports were locked in drawers. and the world's steam speed record still stands on his exhaust nozzle. There is a question worth sitting with after you've heard this story. How many engineers are sitting in workshops right now, in railways, in medicine, in energy, in any field you care to name, who have found something real, printed numbers that cannot be argued with, and been quietly handed a new assignment that removes everything that made their discovery matter? Chapelon's answer to that question was to keep working, to keep measuring, to write it all down in a book, La Locomotive à vapeur, that became the definitive scientific text on steam engineering and is still read today. He let the dynamometer car speak, even when nobody was listening. Somewhere right now, someone is being ignored for proving something that actually works. If this story made you think of another engineer who was right too soon, leave their name in the comments. Some of the best conversations start with the ones history forgot.